everybody. This is Dr. Deljo here to present elementary set theory as part of naive set theory. Now, requirement. Any elementary textbook on set theory or elementary algebra, any sham outline series textbook on varsity algebra, calculus, or probability theory will do. My audience, I expect this to be of interest to senior secondary school mathematics examination preparatory students, pre-varsity algebra students, pre-varsity real analysis students, researchers into naive, raw, fuzzy, set theories that may take this as part of their review when starting off. Anybody that is interested in set theory. This is one of a series of 3 lectures on set theory. Happy listening. Now, let's look at the scope and synopsis. At the end of this lecture, altogether, at the end of the 3 lecture series, I expect my audience to have known the meaning of set, its membership, finite and infinite set, cardinality, I expect them to have known all these things that I've listed. Well, let's start with the meaning of set and its membership. Meaning of set, a collection of objects which possess a unique characteristic and yet distinguishable from each other. Well, membership, a set is defined if whenever any object is given, it is possible to decide whether or not it belongs to the set by using the unique characteristic. Note, the objects in a given set are known as its members. The number of distinct objects in a set is known as its cardinality. However, the set needs to be finite for its cardinality to exist. Examples, the books in a library, they constitute a set. If you pick any book and it doesn't belong to that library, then it's not a member of the set. The cars at the park, they constitute a set. Any car that can't be found in that park, then it's not a member. So note, a set which has a finite number of elements is known as finite set. Otherwise, it is said to be infinite, i.e., it is either not countable or one cannot finish counting its elements. It's customary to use capital letters, that is capital A, capital B, capital C, to denote set, and small case letters, small a, small b, to denote their elements. A set can be specified by listing its elements or describing them. Even description can be verbal or mathematical. A set that has a single element is sometimes called singleton. Those with 2 elements are known as doubleton. Other example, a set of even numbers between 2 and 10 inclusive. That's let A be said that. And B, let it be a collection of x's such that x is equal to 2n, where n is equal to 1, 2, 3, 4, 5. Let's see B, a set containing 2, 4, 6, 8, 10. Note, the sets in examples 1, 2, 3 are equal. They are all equal. It's just that A is specified verbally, and B is specified mathematically, and C is specified by listing. A set may have sets as its elements. I mean set as its element as against having ordinary elements as its elements. Now, a popular example is the power set. An easy example is this, for instance. This is a set, this is a set, that's a set, yet there are elements inside the set D. Where D has its elements as this, you see. Okay, symbols on sets. Well, there are 1001 symbols possible in set theory. Well, sometimes even the algebraists will come up with a symbol, but whenever he does that, he will have explained it, talked about it in his glossary of terms. He will have listed it in his glossary of terms at the beginning of the work. So all these ones, elements such that for all there exists, therefore, since, negation, and conjunction and, disjunction or, union, intersection, contained in and equal to, contains and equal to, null, infinity, implies, is implied, implies and is implied, plus and minus, less than or equal to, greater than or equal to, equivalent, approximately equal to, product. The list is very large. So, but what is of importance again here, sometimes you see a symbol and you see a slash over it. Customarily, the slash negates the symbol. Right? This is membership, this is non-membership. Okay. All right, construction of statement itself. The symbols are the tools with which statements are constructed. For example, a statement such as X is an element of this set implies that the set from X, the singleton, is contained in this set. That's commonsensical. Okay. The pair of brackets, this is included to assist the beginner. So it means these brackets may not be there. You may be reading a text and these brackets will not be there. The content of the first bracket constitutes the premise for the conclusion, which is contained in the second bracket. Sometimes the premise is more than one. Then the use of connectors, such as the and symbol, the or symbol, the union, the intersection, will be utilized. Equality of sets. Any pair of sets A and B are said to be equal if and only if. Mind it, IFF is read as if and only if. A is contained in B and B is contained in A. That is, A is contained in B and B is contained in A implies that A is equal to B. Well, some will say that ought to be, implies that, and is implied, and just mean to be as simple as possible. That's why. So the statement is read if and only if, like I explained. Also, set and logic constitute algebra 1. In the synopsis of algebra, all the set symbols are valid algebraic symbols. I may also write that there is this uniquely. I may also write some symbols, and that will mean that there exists uniquely. Okay, theoretical proofs of equality of sets sometimes require the use of De Morgan's laws, which in the simplest form are this pair. The universal set and complementation. The set containing all the elements under investigation in a particular problem is known as the universal set and is denoted by the symbol U, capital U. Well, some will have it as script U, script that is capital U, that is, it is not unique in the sense that it changes from one problem to another. For instance, if E is the set of even numbers between 2 and 20 inclusive, O, capital O, that is the set of odd numbers between 1 and 19 inclusive. Then B, which is this, 1, 2, 3 from set of naturals from 1 to 20, and this, which is the entire set of naturals, can be the universal set of the sets E and O. More universal sets exist for them. These are not the only universal sets you can construct from these two. Okay, complementation. Given a set capital A, then the set which contains all elements not inside it, but inside its universal set, constitutes the set called the complement of A. It is denoted by A prime or A raised to power C. That is collection of x's, such that x is in the universal set, but x is not in A. Okay, examples. Let U be this and A be that. Then A prime, find A prime, A double prime. U not A, A not you. Note, if I write A minus B, it should be read as set A not set B. It is the set difference of B from A. Solution, even though, so A prime, something that you can find in the universal set, but not this A, this. A double prime, priming, complementation cancels out. A double prime comes back to A. Now, U not A is like A prime. A not U is same as null because there does not exist any element that will be inside A and will not be inside this in a universal set. Then definition. By definition, A prime is U not A. Then the null set is A not U. Now, U prime is null. Any set, any pair of sets AB that do not have any elements in common are said to be disjoint. In some texts, they will say they are mutually exclusive. So they are either disjoint or mutually exclusive. One-to-one correspondence and equivalence set. If to each element of a set, capital D, there corresponds an element of another set, capital B, and vice versa, the elements of the two sets are said to be in one-to-one correspondence. The sets are then said to be equivalent. The symbol for equivalence are these or this. Well, or some other symbols that the algebraists choose to specify for it. That is, if you see A this, it should be read A is equivalent to B. The equivalence, note, the equivalence relation is popular in algebra. Whenever there are three or more sets, whenever three or more sets possess the relationship, they will be reflexive, symmetric, and transitive to one another. Examples. The set A, which is this, B, that are equivalent because for any B that you pick, there exists an A in capital A such that B will be equal to 2 of A, I mean 2 times A. And for all A that you pick in A, there exists B in B such that A will be equal to B over 2. Both B equals 2A and A equals B over 2 define one-to-one correspondences between the sets capital A and capital B. Hence, A and B are equivalent. So the set capital A, which is this, capital N, that are not equivalent. Because even though we can pair all the elements of A with some elements of in N, the reverse procedure leaves one element without a pair. Continuity. Expect set too soon. See you then. Bye for now. Thanks for listening.